Hello there, and welcome to the Sleepy Space Channel. We may have chosen the wrong planet. Venus is nearer than Mars, quicker to reach, and it receives about 4 times the sunlight. Its atmosphere blocks radiation almost as well as Earth's does, and its gravity is 9/10 of the weight you are carrying right now, against barely a third on Mars. Its surface would destroy anything we sent down to it. But 50 kilometers above that surface, there is a band of air at exactly Earth's pressure, warm enough to work in, where a city could float on nothing but the breathable air inside it. Tonight, we set the two worlds beside each other, honestly, and ask why only one of them has ever been planned for. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But none of this is something you need to carry tonight. Venus has held that quiet band of air for hundreds of millions of years, and it will hold it through the night. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The world we decided was hell. There is a planet next door that is almost exactly the size of this one. It has nearly the same mass, nearly the same density, and very nearly the same gravity. It formed from the same material, in the same disk, at the same time, and for most of its history, it may have looked like a place we would recognize. It is the closest planet to Earth. It is the brightest thing in our night sky after the moon. And in every serious conversation about where human beings might one day live, it is not mentioned at all. The planet is Venus, and the way it vanished from our plans is one of the stranger patterns in the history of exploration. We have made Mars the destination. Presidents have named it. Space agencies have built long-range roadmaps around it. Private companies have been founded on the promise of reaching it. There are rovers on its surface with millions of followers, and a small helicopter that flew in its thin air, and a steady stream of photographs of rust-colored ground that have made a distant world feel like a familiar landscape. Venus has none of that. It has no crude mission plan, no flag date, no roadmap. What it has instead is a reputation, and the reputation is a single word: hell. That word attached itself to Venus decades ago, and it has never come off. The unsettling part is how little that reputation reflects the actual arithmetic. When you set the two worlds side by side and compare them on the things that decide whether a human body can survive somewhere, Venus wins most of the categories. It is closer. It is easier to reach. It has 4 times the available sunlight. It has vastly better protection from radiation, and it has gravity that is 9/10 of Earth's, against Mars, which has barely more than a third. That last number is the one that matters most, and it is the one that gets discussed least. So this is the question we are going to spend the next 2 hours with, slowly and without hurry. If we were choosing a second home in this solar system on the merits alone, and no one had already decided for us, would we be going to Venus instead? To understand how the choice got made, it helps to understand how each planet acquired its reputation, because neither one was earned by measurement. Mars entered the popular imagination long before anyone knew anything reliable about it. Early telescopic observers, straining at a small orange disk, sketched networks of straight lines across its surface and called them canals. The word carried an implication that was impossible to unhear. Canals are built. Canals imply engineers. For half a century, Mars was understood by a great many people as a dying world whose inhabitants were moving water from the poles toward the equator in a last, patient effort to survive. That story was wrong in every particular, but it was extraordinarily good storytelling, and it lodged itself deep. By the time spacecraft arrived and found a cold, dry, cratered surface with no canals and no engineers, the imaginative work had already been done. Mars was a place with a narrative attached. Every generation of science fiction that followed reinforced it. And when space agencies needed a long-horizon goal, something distant enough to be worth a career and near enough to be plausible, Mars was already sitting there, preloaded with meaning. Venus took the opposite path. Because it is permanently wrapped in an unbroken layer of cloud, no telescope has ever seen its surface directly. For centuries, it was the one planet in the inner solar system whose face was entirely hidden, and into that blankness people poured the most generous assumptions available. Venus was closer to the sun, so it would be warmer. It was cloudy, so it must be humid. Warm and humid suggested a world of swamps and rainforests and enormous slow-moving life. This was not a fringe idea. It was the mainstream expectation among people who thought carefully about planets. Then the first probes went. They found something that could not have been further from a jungle. Surface temperatures around 460 degrees Celsius, hot enough to melt lead. Surface pressure around 92 times what we feel at sea level here, equivalent to standing 900 meters deep in the ocean. An atmosphere almost entirely carbon dioxide, wrapped in clouds of concentrated sulfuric acid. Landers built like deep-sea submersibles that survived for less than 2 hours before falling silent. The disappointment was proportional to the hope, and it was total. Venus went, in the space of a few years, from a possible second Earth directly to a synonym for the worst place imaginable, with no intermediate stage. There was no period in which people asked whether some part of it might still be useful. The verdict was delivered once, and the case was closed. It is worth noting how strange that closure is, given how much attention Venus received beforehand. Venus was the first planet any spacecraft ever flew past. It was the first planet whose phases were observed through a telescope, and those phases were a direct piece of evidence that the planets circle the Sun rather than the Earth. It is bright enough, at its best, to cast a faint shadow on a dark night with no moon. In the early decades of interplanetary flight, far more machines were sent toward Venus than toward Mars, simply because it was nearer and the trips were shorter. We went there first. We went there often, and then we stopped. The same pattern shows up closer to home, which suggests it is something about us rather than something about Venus. The floor of Earth's own ocean is mapped in less detail than the surface of Mars, and one reason is that there is no way to walk on it and stay. Free-flying habitats in empty orbit, which avoid several of the hardest problems of settling a planet, attract a fraction of the popular enthusiasm that surface bases do. Wherever there is ground to stand on, our plans gather. Wherever there is not, they thin out. And here is where a quieter bias comes in, one that has been shaping human exploration for centuries without being named. We have an obsession with landing on things. Arrival, in our instinct, means standing on a surface. Orbiting does not count. Flying over does not count. Floating above certainly does not count. If you have not put your weight on the ground and planted something in it, some part of us does not accept that you have really been there. This instinct is inherited from the age of ocean voyages, when reaching a place genuinely did mean putting a boat on a beach, and it has followed us into space without ever being examined. Call it surfacism, for lack of a better word. It is the assumption that the interesting part of a world is the part you can walk on. Venus has a surface. It is rocky, volcanic, roughly the same area as Earth's, with 2 continent-sized highland regions and mountains taller than any of ours. It is a real place with real geography. But it is a place no human being will ever stand on, and under the logic of surfacism, that disqualifies the entire planet before the comparison starts. The counter-argument is simple, and once you hear it, it is difficult to unhear. The surface of a planet is not automatically the part of it that suits us. On Earth, we live in an extremely thin shell at the bottom of our atmosphere, not because the ground is sacred, but because that happens to be where the pressure and temperature suit a human body. We are not surface creatures by principle. We are pressure and temperature creatures, and on Earth, the right pressure and temperature happen to sit at ground level. On Venus, they do not. On Venus, the band of air where the pressure and temperature suit us sits about 50 kilometers above the ground. The ground is still down there, still hot, still crushing. But the habitable layer of that planet is simply somewhere else, and there is no law of nature that says a habitable layer has to rest on something solid. That single reframing is what the rest of this video is built on, and it changes the comparison completely. Because once you stop insisting on standing, Venus stops being hell and becomes something much stranger and much more interesting. It becomes a world with a narrow ribbon of air running around it, at exactly 1 atmosphere of pressure, at a temperature you could work in, with almost Earth-normal gravity, drenched in sunlight, shielded from radiation by 50 kilometers of air overhead. There is nothing else like it anywhere in this solar system. We will get to that layer in detail and to what it would mean to build in it. But it is worth sitting for a moment with how thoroughly the alternative has been overlooked. There has never been a crewed mission to Venus proposed as official policy by any nation. There has never been a competition to select volunteers for a one-way trip. There has never been a public campaign, a documentary series, a rover with a following. There have been serious engineering studies. Detailed ones, some of them decades old, describing crude flybys and floating outposts in real technical language, with mass budgets and trajectory analyses and materials specifications. They exist. They are simply not part of the conversation, and they have never had the cultural weight of the alternative pushing behind them. So the picture we are starting from is this. 2 planets, both next door, both hostile in different ways. One of them has a surface we can stand on, a gravity that will slowly take our skeletons apart, and a level of radiation that would put every settler on a lifetime dose budget. The other has a surface that would destroy anything we sent to it within the hour, and 50 kilometers above that surface, the most Earth-like conditions found anywhere off Earth. We chose the first one. This is the story of what we might have chosen instead. Part 2. 2 worlds, measured. Before any argument can be made in either direction, the 2 planets need to be set down beside each other and described plainly. Numbers are the only way to do that honestly, and both worlds have been measured carefully enough that the comparison is not a matter of opinion. Start with Venus. Its diameter is about 95% of Earth's, which makes it the closest match in size to our own planet that exists anywhere in this solar system. Its mass is about 81% of Earth's. Because size and mass are both so close, its internal structure is thought to be broadly similar to ours as well, with a metal core, a rocky mantle, and a crust of silicate rock. If you could somehow lift the atmosphere away and look at the 2 planets as bare spheres, you would be looking at siblings. Surface gravity on Venus is about 9/10 of Earth's. A person who weighs 70 kilograms here would weigh about 63 there. That difference is small enough that most people would not reliably notice it, and small enough that the human body would have no reason to treat it as an abnormal environment. Everything else about Venus is the atmosphere. The surface temperature is around 460 degrees Celsius, and it is essentially uniform. There is no meaningful difference between the day side and the night side, or between the equator and the poles. This is not because Venus is spinning quickly and mixing heat around. It is spinning extraordinarily slowly. It is because the atmosphere is so massive that it functions as a single enormous thermal reservoir, and it simply moves heat faster than the planet's rotation can create a difference. The surface pressure is around 92 times what we feel at sea level here. That is the equivalent of being about 900 meters below the surface of the ocean, deeper than the crush depth of any military submarine ever built. The composition is about 96% carbon dioxide, with most of the remainder nitrogen. And because the whole atmosphere is so massive, that small nitrogen fraction still adds up to several times more nitrogen than Earth has in total. Venus holds more of the gas we breathe as a buffer than our own planet does. Above all of that sits an unbroken deck of clouds made of concentrated sulfuric acid, which reflects most of the incoming sunlight straight back to space. That reflectivity is why Venus is so bright in our sky, and it is also why the surface below is lit only dimly, in a heavy orange light like a very overcast afternoon. The rotation is the strangest single fact about the planet. A day on Venus, measured as one full turn, takes around 243 Earth days, which is longer than its year. And it turns backwards relative to almost everything else in the solar system, which means that if the sky were ever clear enough to see, the sun would rise in the west. It has no moon. It has no global magnetic field generated in its interior, and it has nothing resembling the plate tectonics that continually recycle Earth's crust. Now set Mars beside it. Mars is small. Its diameter is about half of Earth's, and its mass is about 1/10. That difference in mass is the root of nearly every problem Mars has, because mass is what holds an atmosphere down and what keeps an interior warm enough to run a magnetic dynamo. Surface gravity on Mars is about 38% of Earth's. Our 70-kilogram person would weigh about 26 kilograms there. That is a difference nobody could fail to notice, and it is the difference we will spend a whole part of this video on. The surface temperature averages around -60 degrees Celsius. On a summer afternoon near the equator, it can climb above freezing at ground level. On a winter night near a pole, it can fall below -120. The atmosphere is about 95% carbon dioxide, which sounds similar to Venus until you look at how much of it there is. Martian surface pressure is about 0.6% of Earth's. That is not thin air. That is very nearly no air at all. It is worth being precise about what that means for a human body, because the cold is not the immediate problem. At Martian surface pressure, water boils at body temperature. An unprotected person on Mars would not freeze first. The fluids in their tissues would begin turning to vapor, and consciousness would go in well under a minute. A pressure suit on Mars is not a comfort measure. It is the only thing between a person and a form of failure that has nothing to do with temperature. Mars does have real advantages, and they are substantial. There is water ice at both poles, in enormous quantities. There are buried glaciers at mid-latitudes, some of them hundreds of meters thick. There are hydrated minerals spread across wide regions of the surface, holding water chemically bound into rock. Mars has a day almost exactly the length of ours, 24 hours and about 39 minutes, and an axial tilt close enough to Earth's that it has recognizable seasons. It has 2 small irregular moons. And it has a surface you can drive on, dig into, and build from. It also has a chemistry problem that follows you indoors. The Martian soil contains perchlorate salts at concentrations high enough to be toxic to humans, and the dust is fine, abrasive, and electrostatically charged, so it clings to everything rather than settling off. Every excursion brings some of it back through the airlock. So here is the comparison, laid out in the plainest possible terms. On reachability, Venus wins. On gravity, Venus wins decisively. On available sunlight, Venus wins by a factor of about 4. On radiation shielding, Venus wins decisively. On temperature and pressure, at the altitude where people would actually live, Venus wins. On access to solid ground and mineral resources, Mars wins decisively. On access to water, Mars wins decisively. On room to spread out without building anything new, Mars wins. On what happens when something breaks badly, Mars wins, because Mars has ground to fall back on. On long-term transformation of the whole planet, the arguments run both ways, and neither side is close to being settled. Read that list twice and something becomes clear. This does not produce a winner. It produces a trade, and the trade is remarkably clean. Venus is a better place to be a body. Mars is a better place to build a civilization. Venus gives you the conditions a human being needs and withholds the materials a society needs. Mars gives you the materials and withholds the conditions. That is the honest shape of the comparison, and it is worth holding on to through everything that follows, because the temptation in a question like this is to pick a side and then arrange the evidence behind it. The interesting answer is not that one planet is right and the other is wrong. The interesting answer is that we have quietly assumed one of these trades is obviously better than the other, without ever really examining the other one. A few more details are worth adding, because they say something about how differently the two worlds are put together. Venus receives nearly twice as much sunlight per square meter at the top of its atmosphere as Earth does, and yet its cloud deck sends about 3/4 of that straight back out. The planet is simultaneously the brightest object in our sky after the Moon, and one of the dimmest places to stand in the inner solar system. Both facts have the same cause. The Martian atmosphere is so thin that a significant fraction of it seasonally condenses. Each winter, carbon dioxide freezes directly out of the air onto the winter pole as frost, and the total atmospheric pressure across the whole planet drops by something like 1/4. Then it sublimates back in spring, and the pressure comes up again. The entire atmosphere of Mars breathes in and out once a year. Mars has the largest volcano and the longest canyon system anywhere in the solar system. Both are genuinely magnificent, and neither improves habitability by a single percentage point. Venus, for its part, has over 1,000 identified volcanic structures, including broad, flat domes formed by unusually thick lava spreading out under enormous pressure, and long channels carved by flowing rock that run for hundreds of kilometers. There is also the matter of what each planet lost and how. Venus today is extraordinarily dry, holding only traces of water vapor in its air and none at all on its ground. But the hydrogen still present in its atmosphere carries a chemical signature that points backward. Heavy hydrogen, the slightly weightier version of the same element, is enriched there far beyond what we see on Earth. Light hydrogen escapes to space more easily than heavy hydrogen does, so an enrichment like that is the fingerprint of an enormous amount of water having been lost, molecule by molecule, over a very long time. Venus is not a world that was born dry. It is a world that evaporated. Mars lost its air by a different route. It was small enough that its interior cooled relatively quickly, and when the churning metal core slowed, the magnetic field it generated faded with it. Without that field, the solar wind had direct access to the top of the atmosphere and stripped it away steadily across hundreds of millions of years. Both planets ended up with almost nothing that we would find breathable. One of them got there by boiling, and the other by being blown away. And the total land area comparison is closer than it sounds. Mars is half Earth's diameter, so its surface area is about 1/4 of ours. But Earth is mostly ocean, so the dry land on Mars adds up to something close to the total area of all of Earth's continents combined. There is a great deal of room on Mars. There is just very little air over any of it. Part 3. The Crossing. Every argument about settling another world begins with the problem of getting there, and the getting there is where a great many otherwise reasonable plans quietly fall apart. So it is worth walking slowly through what each journey actually involves, because the two crossings are not similar, and the difference compounds through everything that follows. Venus is the nearest planet to Earth. At its closest approach, it comes nearer to us than anything else in the sky except the Moon, closing to something like 40 million kilometers. Mars, at its closest, is roughly 55 million kilometers away, and at its furthest, it is well over 300 million. But raw distance is a poor guide to interplanetary travel, because spacecraft do not travel in straight lines. They change orbits, and what matters is the energy required to make that change and the timing of the windows when it can be done efficiently. The efficient path between two planets is a long, curving arc that touches one orbit at its start and the other at its end. To take that path, you have to leave when the two planets are positioned correctly, and those alignments come around on their own schedule. For Venus, a favorable window opens roughly every 19 months. For Mars, roughly every 26. The crossing times differ substantially. A minimum energy trajectory to Venus takes on the order of 4 months. A minimum energy trajectory to Mars takes on the order of 6 to 9. The energy required is comparable for both, with Venus slightly cheaper, which is a quiet advantage that translates directly into either less fuel or more payload. Where the two really separate is in what a full round trip looks like. Because of how the windows line up, a crew going to Venus and coming back can complete the whole expedition in roughly a year to a year and a half, including a stay at the destination. A crew going to Mars faces a harder choice. Either they stay on the surface for around 18 months waiting for the return window to open, making the total mission close to 3 years, or they take a faster and far more expensive trajectory that costs a great deal of additional energy for a much shorter stay. There is one more trajectory advantage at Venus that has no equivalent at Mars, and it is worth pausing on. It is possible to leave Earth on a path that swings past Venus, is bent by Venus's gravity, and returns to Earth without any engine firing at all along the way. The whole loop is a single, unpowered arc. This is called a free return, and it means that a crewed Venus flyby is naturally abort-tolerant. If something goes wrong after departure, the ship is already on a path that brings everyone home. Nothing has to work for that to happen. It is simply the shape of the orbit. Crewed Venus flyby missions have been studied in real engineering detail on exactly this basis, as a way of gaining deep space experience with a shorter duration and a gentler risk profile than a Mars mission would carry. Those studies were done and shelved, not because they failed, but because Venus was not the destination anyone wanted. The practical consequences of a shorter crossing run through every part of a mission. Less time in transit means less food, water, and air to carry, which means less mass, which means less fuel, which means lower cost, which means more of the budget can go into the thing you are actually trying to build. It means less radiation accumulated in deep space, where there is no planet or atmosphere providing any shelter at all. It means less time spent weightless, with everything that does to a body. It means fewer months during which a piece of hardware can fail, with no possibility of repair or resupply. And it means a shorter window during which a crew is beyond any help. That last point deserves emphasis. On a Mars crossing, there is a stretch of many months during which a serious medical emergency has no answer. There is no turning around, no rescue, no faster path home. The same is true of a Venus crossing, but the stretch is shorter, and the windows to send help behind you come around more often. There is a quiet irony in how often we already go to Venus without meaning to. Venus is the most heavily used gravitational slingshot in the inner solar system. Spacecraft bound for Mercury swing past it, sometimes more than once, to shed the enormous speed that falling toward the Sun would otherwise give them. Spacecraft bound for the outer planets have used it to gain speed on the way out. Missions to study the Sun itself have looped past Venus repeatedly to tilt their orbits and climb out of the plane the planets share. Over the whole history of interplanetary flight, more spacecraft have flown past Venus than have ever been sent there as a destination. We use it constantly as a corner to turn around, and almost never as a place to arrive. The radiation arithmetic of the crossing is worth stating plainly as well, because it is not intuitive. On a mission to Mars, the dose accumulated during the voyage out and back is comparable to the dose accumulated during the entire stay on the surface. Deep space between planets is the most exposed environment a crew will ever occupy, with no atmosphere and no magnetic field of any kind between them and the sky. This means that shortening the transit is not a convenience. It is one of the most effective radiation countermeasures available, and it costs nothing to implement, because it is simply a property of where you are going. A 4-month crossing carries roughly half the deep space dose of an 8-month one before anyone builds a single shield. Then there is the arrival, and here the difference becomes almost comic. Arriving at Mars is notoriously difficult, and the reason is that its atmosphere sits in the worst possible middle ground. It is thick enough that a vehicle arriving at interplanetary speed will burn up without a heat shield. But it is far too thin to slow a heavy vehicle to a safe landing speed on its own. Parachutes work poorly in air that thin. So every Mars landing has to combine aerodynamic braking, parachutes that are only partly effective, and rocket engines firing downward through the final seconds, all in a sequence that must execute perfectly, automatically, with the planet too far away for anyone on Earth to intervene in real time. The margins are narrow enough that the mass any single vehicle can put on the Martian surface is one of the hardest limits in the whole field. Venus inverts the problem entirely. Its atmosphere is so deep and so dense that aerodynamic braking does essentially all the work. A vehicle arriving at Venus can shed its interplanetary velocity against 100 kilometers of increasingly thick air, and then simply stop descending when it reaches the altitude where it floats. There is no touchdown. There is no landing sequence. There is no final rocket burn timed to the second. The vehicle enters, slows, deploys, fills, and comes to rest in the air. The entry corridor at Venus is also unusually forgiving, because the atmosphere is deep and its density changes gradually with altitude, which gives a wide range of acceptable approach angles rather than a knife edge. And because a floating habitat never experiences a touchdown load, an entire category of structural requirement disappears from the design. Nothing has to survive impact, because nothing ever impacts. There is a cost on the other side of the ledger, and it is real. Leaving Venus is harder than leaving Mars. Venus has nearly Earth's gravity, which is wonderful for living in and expensive to climb out of. A return vehicle would have to launch from a floating platform rather than from firm ground, which is an unfamiliar engineering problem. Some architectures handle this by leaving the return craft in Venus orbit and sending up only a small ascent stage from the cloud layer, launching from an altitude where the air is thin enough not to fight the rocket much but thick enough to help with the first part of the climb. That is a solvable problem, but it is a genuine one, and it is the strongest single argument for Mars in this section. Communication is the last piece. Radio signals take about 5 minutes to make the round trip to Venus at closest approach. To Mars, the round trip runs from about 8 minutes at best to over 40 at worst. That difference sounds technical, but it shapes daily life. At Venus, something close to a strained conversation is possible with Earth. At Mars, conversation is impossible in principle. Every exchange is a message with a weight attached, and every decision has to be made locally. Both planets pass behind the Sun periodically, producing communication blackouts when the star sits directly between them and Earth. Venus's blackouts are shorter. And because Venus's transfer windows come around every 19 months rather than every 26, an emergency resupply, a spare component, or a follow-on crew can be dispatched sooner after a problem is identified. One honest disadvantage on the way to Venus: the thermal environment is harsher. A spacecraft heading inward is moving toward the sun, and sunlight grows stronger the whole way. Radiators have to be larger, shading matters more, and thermal control becomes a more demanding part of the design than it is on an outbound cruise to Mars, where the sun is fading behind you. Set all of it side by side, and the crossing to Venus is shorter, cheaper, more frequent, more forgiving on arrival, better connected to Earth, and harder to leave. That is a good trade for a place you intend to stay. Part 4. The weight of a body. Of all the differences between these two worlds, one stands apart from the others, and it is the one that receives the least attention. Air can be manufactured. Water can be mined, or imported, or pulled out of chemistry. Radiation can be blocked by putting enough mass overhead. Temperature can be managed with insulation and power. Every one of those is an engineering problem, and engineering problems yield to time and effort. Gravity does not. Gravity is a property of the planet itself, set by how much material went into building it 4.5 billion years ago. Short of moving mountains of matter into the crust, there is nothing whatsoever to be done about it. Whatever gravity a world has is the gravity it will have for as long as anyone lives there. Venus has about 9/10 of Earth's. Mars has about 38%. That is the whole comparison, and everything that follows is about why it matters more than it sounds like it should. Almost everything we know about the human body in reduced gravity comes from weightlessness, which is the extreme end of the scale. Decades of long-duration orbital flight have produced a consistent picture, and it is not a gentle one. Bone is the clearest effect. In weightlessness, the weight-bearing bones of the body begin losing mineral density at a rate of roughly 1 to 2% per month. The loss is concentrated exactly where you would expect, in the hips, the pelvis, the lower spine, and the legs, which are the structures that exist specifically to carry a body against gravity. Bone is living tissue that constantly rebuilds itself in response to load, and when the load disappears, the rebuilding slows while the dismantling continues. To put that rate in perspective, it is roughly 10 times faster than the bone loss seen in advanced age-related bone disease on Earth. A person in orbit for a year loses skeletal mass at a pace that would take a decade or more to accumulate down here. Muscle goes the same way, and faster. The postural muscles along the back and legs, which exist almost entirely to hold a body upright, atrophy quickly when there is no upright to hold. The heart follows, because the heart in weightlessness no longer has to push blood upward against weight. It becomes measurably smaller and less capable of the ordinary work of standing. Fluids inside the body shift as well. On Earth, gravity holds a meaningful fraction of the blood and other fluids in the lower body. Remove that, and they redistribute upward toward the chest and head. This produces the puffy faces and permanent sinus congestion familiar from orbital footage, and it also produces something less visible and more serious. The pressure inside the skull rises, and that pressure presses on the back of the eyeball, flattening it slightly and swelling the optic nerve where it enters. A majority of long-duration crew members experience measurable changes to their vision as a result, and in some cases, those changes do not fully reverse after coming home. Kidney stones become substantially more likely because all that calcium leaving the bones has to leave the body somehow, and the route it takes is the urinary tract. The immune system shifts in ways that are still being characterized, with dormant viruses reactivating more often and immune cell behavior altered for weeks after return. Balance and coordination degrade because the gravity-sensing organs of the inner ear stop receiving the signal they spent millions of years evolving to interpret. Countermeasures exist, and they help. Intensive resistance exercise, using specialized equipment, performed for around 2 hours every single day, can hold bone loss down to a fraction of the untreated rate. It does not eliminate it, and it consumes a large share of the crew's waking, productive time, every day, indefinitely, forever. Some of the smaller changes are the most telling because they show how completely the body is shaped by weight. The fluid shift begins within hours of reaching orbit, not days. The spine lengthens by several centimeters as the discs between the vertebrae decompress, so crew members return home measurably taller than they left, and often with back pain from the stretching. The skin on the soles of the feet softens and peels away, because nobody is standing on it, while calluses form across the tops of the feet instead, where they hook under restraints to hold position. The sense of smell dulls in the first weeks because of the congestion, and crew members coming back from long missions are typically carried from their capsules, not because they are injured, but because standing upright has become genuinely difficult. There is also an interaction that gets overlooked. Bone loss and radiation exposure compound each other. Weakened bone fractures more easily, and accumulated radiation raises long-term cancer risk in the very marrow that bone protects. Neither countermeasure helps with the other problem. Exercise does nothing about cosmic rays, and shielding does nothing about mineral density. That is the picture at zero. Now, here is the part that ought to be discussed far more often than it is. Nobody knows what happens in between. No human being has ever lived for an extended period at any gravity between 0 and 1. Every data point we possess sits at one end of the scale or the other. The lunar surface stays lasted days, not months, and they were far too short to measure anything meaningful about long-term adaptation. There is a wide, empty region in the middle of the graph, and 38% of Earth's gravity sits directly in it. This means that when anyone states confidently that Martian gravity will be survivable over a lifetime, they are not reporting a finding. They are making an assumption, and there are two competing versions of that assumption with nothing to choose between them. The first is what might be called the threshold model. It holds that the body's load-bearing systems are essentially switches, that they respond to the presence of meaningful weight rather than to its exact amount, and that 38% of Earth's gravity is enough to keep those systems switched on. Under this model, a settler on Mars loses a little bone early, stabilizes, and then lives more or less normally. The second is the proportional model. It holds that the body responds to the actual load it carries, and that a third of the load produces something like a corresponding fraction of the weightless decline. Slower than orbit, perhaps 60% of the orbital rate, but continuing. Under this model, there is no plateau. Bone density falls year after year, gently and without pause, for as long as a person remains there. If the second model is right, then a Martian settlement is a place where people quietly come apart over decades. And the consequence extends to anyone born there. This is where the question becomes something other than a medical curiosity. A settlement only becomes a civilization when children are born into it and grow up healthy. Almost nothing is known about mammalian development at reduced gravity. The animal work that has been done in weightlessness has found disruptions to bone formation, to the development of the balance organs, and to the way the cardiovascular system patterns itself. Whether a third of a gravity is enough for a human skeleton to form correctly is simply an open question, and it is not the kind of question that can be answered in advance by any ethical experiment. The shape of a growing skeleton is written partly by the forces acting on it. Bone lays itself down along the lines of stress it experiences, which is why the bones of a person who runs are different from the bones of a person who swims. A child growing up under a third of Earth's weight would grow a skeleton adapted to a third of Earth's weight, and there is no reason to expect that skeleton to be capable of carrying a full one. The balance organs of the inner ear calibrate themselves against gravity during early development. A person raised on Mars might never develop a sense of balance appropriate to anywhere else. The cardiovascular system establishes a pressure gradient suited to the environment it grows in. A Mars-born adult standing on Earth for the first time might faint from the simple effort of remaining upright. The plain version of all this is that a Mars settlement might be a place people can visit for years but never fully belong to, and that the first generation born there could be permanently unable to come to the world their parents left. At 9/10ths of a gravity, every single one of these questions simply evaporates. There is no threshold debate at Venus, because 9/10ths is not near any threshold, it is nearly the full value. There is no generational uncertainty, because a child would develop under conditions almost identical to those of a child on Earth. There is no need for 2 hours of daily resistance exercise, because there is nothing to counteract. A person standing in a habitat floating above Venus weighs about what they weigh at home. Their bones receive the load they evolved to receive. Their heart works against the pressure it expects, and their body has no reason to know it has left. That is not a small advantage. It may be the largest single advantage any destination in this solar system has over any other, and it is almost never the headline. It is worth adding one more thing. Artificial gravity is possible, but only by spinning, and you cannot spin the surface of a planet. A rotating habitat in free space or in orbit can generate whatever effective weight its designers want. A settlement on the ground on Mars cannot use that trick at all, except by building dedicated centrifuges and having people take turns inside them. Sleeping in a centrifuge has been proposed as a partial fix, on the theory that 8 hours of full weight each day might be enough to preserve bone. It has never been tested in humans over any meaningful duration, and it remains an idea rather than a solution. The Moon offers a nearer place to begin answering these questions, at 1/6 of a gravity, close enough to Earth that people could be brought home quickly if something went wrong. Any honest, long-term Mars program depends on that answer more than it depends on any rocket. And until it comes back, the confident statements about Martian gravity remain what they have always been. Hopes, stated in the grammar of facts. Part 5. Light, Power, and the Moving Sky. Nothing happens in a settlement without power. Air is recycled with power. Water is purified and manufactured with power. Food is grown under lights. Temperature is held steady. Waste is processed. And every machine that keeps a closed environment closed runs on the same supply. A settlement's power budget is not one system among many. It is the thing that all the other systems are made of. So the amount of sunlight falling on a place is not a detail. It is close to the foundation. Venus orbits at about 72% of Earth's distance from the Sun. Mars orbits at about 1.5 times that distance. Sunlight weakens with the square of distance, so those two modest-sounding numbers open up into something much larger. At the top of Venus's atmosphere, sunlight arrives at roughly 1 9/10 times the intensity we receive here. At Mars, it arrives at roughly 43%. The ratio between them is around 4:1, and it is 4:1 before anything else is taken into account. Inside the Venusian cloud tops, sunlight remains abundant. And there is a bonus that exists nowhere else. The cloud deck below is highly reflective, sending most of the light that hits it back upward. A habitat floating within or just above that deck therefore receives light from beneath as well as from above. A solar array on such a habitat can be built double-sided and remain productive on both faces. There is no other location in the inner solar system where that arrangement makes sense, and it effectively adds to an already generous energy supply. There is no dust in that environment to settle on the panels. There are no seasons to swing the output up and down across the year. There are no storms in the terrestrial sense, no fronts, no weather systems building and collapsing. The sunlight is simply there, continuously, at nearly twice terrestrial strength, in a place that does not change much. Mars has close to the opposite situation, and its power problem is one of the most persistent difficulties in every serious settlement plan. The baseline is already low, at less than half of Earth's sunlight. Then there is dust. Fine Martian dust settles continuously onto any exposed surface and reduces solar output steadily between cleanings. Several robotic missions have ended not because anything broke, but because accumulated dust finally starved the spacecraft of power. Occasionally, a passing dust devil has swept a panel clean by chance and given a mission years of extra life, which is a wonderful thing to happen and not something anyone can plan around. Then there are the great storms. Every few Martian years, a regional dust storm grows until it wraps the entire planet, and the sky fills with suspended particles for weeks or months at a time. During those events, sunlight reaching the surface drops by a large fraction. A settlement running on solar power would face an extended period of severely reduced output, with no way to know in advance how long it would last. And the long, cold Martian night imposes its own load. Overnight temperatures fall far enough that keeping equipment and people from freezing consumes serious energy, which means the demand peaks precisely when the supply is zero. For all these reasons, most credible Mars architectures do not rely on sunlight at all. They assume nuclear fission reactors on the surface as the primary power source. That is a workable answer, and small surface reactors have been developed and tested for exactly this purpose. But it adds mass to be launched, complexity to be maintained, a fuel supply chain reaching back to Earth, and a category of risk that solar panels do not carry. A floating habitat in the Venusian cloud layer, drifting in continuous strong sunlight, with no dust and no seasons, has arguably the most benign power environment of any settlement site off Earth. That is a strange sentence to write about the planet we call hell, and it is accurate. Which brings us to the sky itself, and to one of the more beautiful facts about how a Venusian settlement would experience time. The Venusian surface turns very slowly. A single rotation takes around 243 Earth days, longer than the planet's year, and it turns backwards. Taken at face value, that would seem to condemn any settlement to 4 months of unbroken daylight, followed by 4 months of unbroken dark, which would be difficult for both power systems and human beings. But a floating habitat does not have to share the ground's rotation, and on Venus, it emphatically does not. The upper atmosphere of Venus super-rotates. The entire cloud layer circles the whole planet in about 4 Earth days, moving something like 60 times faster than the surface beneath it. Nobody fully understands how this works. How the upper air acquires that much rotation, and how it maintains it against friction with the slower ground below, remains one of the genuinely unresolved questions in planetary science. But it is thoroughly observed, and it has been tracked directly by watching cloud features travel around the planet. A habitat drifting passively with those winds therefore experiences a day and night cycle of roughly 4 Earth days. Around 2 days of light, around 2 days of dark. Longer than what a human body is tuned to, but nothing remotely like a 4-month night. And a habitat that wanted a different rhythm could adjust its altitude slightly to find a different wind speed, or use modest propulsion to drift with or against the flow. The wind speeds involved sound alarming until you think about what wind actually is. In the cloud layer, the air moves at something like 360 kilometers per hour. On Earth, that number describes the strongest tornado. On Venus, it describes nothing at all from inside a floating habitat, because the habitat moves with the air. Wind exerts force only on things that resist it. A free-floating structure is not resisting anything. It is part of the flow. This is worth sitting with, because it is one of the more counterintuitive comforts of the whole concept. A city drifting in the Venusian cloud layer would be traveling at close to 400 kilometers per hour, and inside it, nothing would move. The air would be still. A cup of water would sit undisturbed on a table. Through a window, the only sign of that enormous speed would be a slow procession of golden cloud, going nowhere in particular. The superrotation is also remarkably steady. Earth's atmosphere is turbulent because it is driven by strong temperature contrasts between equator and pole, between land and sea, between day and night. Venus has almost none of those contrasts. Its atmosphere is windy the way a broad river is fast, which is to say smoothly, and in one direction, without the churning that makes terrestrial weather so unpredictable. There are exceptions. Enormous, persistent vortices spin over both poles of Venus, complicated structures that shift and reshape themselves over time. They are the most structurally interesting weather features on the planet, and the most obvious places for a habitat not to be. Avoiding them is a navigation problem, and it is a modest one when the whole rest of the planet is available. Venus also has essentially no seasons. Its axis is very nearly upright relative to its orbit, so there is no summer hemisphere and no winter one, no tilting toward or away from the sun across the year. Combined with a nearly circular orbit and an atmosphere that redistributes heat almost perfectly, this produces a planet whose conditions barely change at all with time. That would be monotonous to live under and extraordinarily easy to design for. Every system could be built for one set of conditions and left there. It is worth saying what the light would actually look like. Inside the cloud deck, visibility is poor, and a window would show golden fog more often than a view. But above the deck, at around 70 kilometers, the sky opens. From up there, the sun is bright and unfiltered, and looking down means looking across an unbroken luminous plain of cloud stretching to a curved horizon, lit from above and glowing. It is one of the few genuinely beautiful environments available anywhere off Earth, and beauty is not nothing in a place where people are meant to spend their lives. The one energy burden Venus does impose is cooling rather than heating, and it runs in the opposite direction to everything a Mars settlement worries about. At the habitable altitude, the outside air is warm rather than cold, so waste heat does not simply radiate away as it does in vacuum or in a Martian night. It has to be actively moved, which means radiators, working fluids, and a continuous power draw that never stops. It is a manageable load with the sunlight available, but it is the reason a habitat that loses power has a problem quickly rather than slowly. Compare that to Mars once more. Mars has an axial tilt close to Earth's, so it has genuine seasons, with a summer and a winter and a spring. Its day is almost exactly the length of ours, which is one of its most underrated advantages, because a human body settles into a Martian day with almost no adjustment. Those are real points in Mars's favor, and they matter for daily life in ways that are easy to underestimate. But Mars pays for its familiar sky with its dust. The particles are extremely fine and carry an electrostatic charge, so they do not settle off surfaces, they cling. They work into seals and joints and mechanisms. They coat visors and panels. And when the great storms come, they take the light away for weeks. So the energy picture ends up mirroring the gravity picture. Venus offers something continuous, generous, and requiring no invention. Mars offers something intermittent, weak, and requiring a nuclear supply chain to compensate. Neither of these is the reason anyone chose Mars. Both of them are reasons someone might not have. Part 6. The roof overhead. Before going on, It is worth gathering up what has accumulated so far, because the pieces have been arriving one at a time and they add up to something. We began with 2 planets and a reputation. Mars, which acquired a story before it acquired data and became the destination by inheritance. Venus, which acquired a different story, lost it violently when the first probes reported back and has been called hell ever since. And underneath both stories, a habit of thought that treats standing on ground as the only real form of arrival. Then we measured them. Venus is almost exactly Earth's size and nearly Earth's weight underfoot, wrapped in an atmosphere that has cooked its surface to the melting point of lead. Mars is small, cold and nearly airless, with water and metal and room to spread out. A clean trade, one world suits a body, the other suits an industry. Then we cross to each. Venus is closer, cheaper, quicker, more frequent, and forgiving on arrival, because its atmosphere does the braking for you. Mars is further, slower, and lands hard, but it lets you leave again more easily. Then we came to weight, which is the one thing that cannot be built. 9/10 of a gravity on Venus, and no questions left to answer. 1/3 on Mars, and a whole empty region of the graph where the answers should be. And then light, which turns out to run 4-to-1 in Venus's favor, in an environment with no dust and no seasons and no storms to take it away. Which brings us to the next thing overhead, and to the hazard that accumulates so slowly that it is easy to forget it is happening at all. Radiation in space comes from 2 directions, and they behave differently. The first is galactic cosmic rays, heavy atomic nuclei arriving from far outside this solar system, traveling at close to the speed of light. They are relatively rare, but each one carries enormous energy, and they are extraordinarily difficult to stop. They are also strange in a way that matters. A thin shield can make things worse, because a heavy nucleus striking a thin barrier shatters into a spray of secondary particles, and the shower on the far side can be more damaging than the single particle that caused it. The second source is the Sun, which periodically releases bursts of energetic particles. These are less penetrating individually, but arrive in enormous numbers, and an unshielded person caught outdoors during a large event could receive a serious dose within hours. Shielding against either is fundamentally a matter of putting mass between a body and the sky. What matters is not the thickness of a barrier, but its total weight per unit of area, usually measured in grams per square centimeter. And this is where the comparison between the 2 planets becomes stark. Earth's atmosphere provides around 1,000 grams per square centimeter of shielding at sea level. 10 meters of water would do about the same thing. On top of that, our planet has a magnetic field generated in its molten core, which deflects a large fraction of the incoming charged particles before they ever reach the air. Mars has no such field, and its atmosphere provides around 16 to 20 grams per square centimeter at the surface. That is roughly 1/50th of what we have here. It is not nothing, and it is enough to make the Martian surface better than open space. But the dose accumulating on an exposed settler is high enough that career limits become a genuine constraint on how long anyone can stay. Venus, at the habitable altitude around 50 kilometers up, still has several hundred grams per square centimeter of atmosphere overhead. That is comparable to what a person receives standing on a high mountain on Earth. Venus also has an induced magnetic field, generated not by a core dynamo, but by the solar wind flowing past its electrically charged upper atmosphere, and that field deflects a meaningful fraction of the lower energy particles before they arrive. The practical result is worth stating in the plainest possible terms. Radiation exposure in a Venusian cloud habitat would be roughly what a person experiences living at high altitude on Earth. Radiation exposure on the Martian surface would be high enough to require dose accounting for every person, every year, for their whole stay. That difference dictates the entire architecture of a Mars settlement. Every credible design puts the habitats under several meters of regolith, or inside natural lava tubes, or behind water tanks arranged as shielding. That is achievable, and it is not exotic. But it defines the character of the place completely. People on Mars would live underground. They would go outside in suits for limited periods, against a budget. The sky would be something they visited, not something they lived under. On Venus, the atmosphere is the shielding, and it is already there. Nothing needs to be buried. Nothing needs to be built. No dose ledger needs to be kept for ordinary daily life. The protection is free, permanent, and installed. And the same atmosphere quietly performs a second service without being asked. Small objects strike planets constantly. Grains and pebbles left over from the formation of the solar system, fragments of asteroids and comets, all of it moving at speeds where even a small mass carries the energy of an explosion. On a world with no air, or almost none, these arrive at full velocity and hit whatever is underneath. Mars stops some of them and not others. Fresh craters appear on the Martian surface regularly, and they are catalogued from orbit as they appear. Any pressurized structure on Mars needs either burial or a dedicated shield against them, because a small hole in a habitat holding one atmosphere against near vacuum is a serious and immediate problem. Venus stops essentially all of them. The atmosphere is so deep and so dense that small impactors are consumed entirely on the way down. The evidence for this is written on the ground itself. The Venusian surface has almost no small craters, because for hundreds of millions of years, nothing small has managed to reach it. Anything below a certain size is destroyed high above, and a habitat floating at 50 kilometers has 100 kilometers of air above it doing that work continuously. So the planet we describe as the most hostile world in the inner solar system provides, at no cost and with no maintenance, the two things a Mars settlement must construct and sustain at enormous expense. A roof against radiation and a roof against impacts. The hostility is real, but it is all pointed downward. From 50 kilometers up, that same hostile atmosphere is doing the protecting. It is worth understanding why cosmic radiation is treated so seriously, because the damage it does is not like the radiation most people picture. Ordinary radiation deposits its energy diffusely, spread thinly through tissue. A heavy nucleus arriving at close to light speed does something different. It punches a narrow track straight through, destroying everything directly along that line and leaving a corridor of damage behind it. Cells adjacent to the track are affected by the secondary particles thrown sideways. The long-term consequences for the central nervous system, where cells are not replaced, are still being worked out, and the honest position is that we do not fully know what a multi-year exposure would do to the way a person thinks and remembers. The dose limits used in human spaceflight are not arbitrary either. They are set to keep the excess lifetime risk of cancer within a few % above the ordinary background risk everyone carries. That is a deliberately conservative standard, chosen for professional astronauts on missions measured in months. Applying it to settlers who intend to stay for decades produces numbers that no amount of careful scheduling can accommodate on an unshielded Martian surface. There is one further protection Venus supplies that rarely gets mentioned. Ultraviolet light from the sun arrives at Venus at nearly twice the intensity it reaches Earth, and it would be a serious hazard to exposed skin and eyes and to any biological system. But the sulfuric acid cloud deck absorbs and scatters ultraviolet heavily. Beneath the cloud tops, that particular part of the spectrum is largely gone. On the Martian surface, by contrast, ultraviolet flux reaches the ground almost unimpeded because there is no ozone layer and very little air, and it is one of the reasons the Martian surface is chemically hostile to organic molecules. A few further details fill in the picture. Water is one of the best practical shielding materials available because it is rich in hydrogen, and hydrogen is unusually good at absorbing the energy of fast particles without producing damaging secondaries. This is why habitat designs so often route water tanks around sleeping quarters, where people spend the most continuous time. Aluminum, by contrast, is a poor shield against cosmic rays for exactly the reason described earlier. Heavy nuclei fragment in it and produce showers. Venus's induced magnetosphere is a curious thing. It is generated fresh, moment by moment, by the solar wind streaming past the ionosphere, with no internal dynamo behind it. It exists only because the wind is blowing. If the solar wind stopped, Venus's magnetic protection would simply vanish within hours. And there is a factor that runs against Venus which should be named honestly. Solar particle events are more intense closer to the Sun, and Venus sits closer. The atmosphere there is therefore working harder than the same depth of air would at our distance. It is still winning comfortably, but it is not winning as easily as the raw numbers suggest. Set against a Martian surface where the dose limits used in spaceflight would be reached in a matter of a few years without shielding, though, it is not a close contest. On one planet, the sky is the danger. On the other, at the right altitude, the sky is the shelter. Part 7. The furnace below. Everything said so far has been in Venus's favor, and it would be dishonest to continue without spending real time on the reason nobody plans to go there. The Venusian surface is, by any reasonable measure, the most immediately lethal environment on any solid body in this solar system. It is worth understanding exactly why, because the specifics matter for what comes afterward. Start with the heat. The surface of Venus sits at around 460 degrees Celsius. That is hotter than the surface of Mercury, despite Venus being nearly twice as far from the Sun, and the entire difference is atmospheric. The mechanism is straightforward and relentless. Sunlight filters down through the clouds, weakened but not extinguished, and warms the ground. The warm ground re-radiates that energy upward as infrared, which is what all warm things do. But infrared is exactly what carbon dioxide absorbs, and there are 92 atmospheres of it overhead. The energy gets absorbed and re-emitted in every direction, including back down, over and over, through kilometer after kilometer of dense gas. Each pass sends some of it back. With no ocean to dissolve the carbon dioxide, and no plate tectonics to bury it in rock, there is no break anywhere in the system. The heat accumulated, and it stayed. There is a detail here that puts the whole thing in an unexpected light. Earth is thought to hold roughly as much carbon dioxide as Venus does, by total quantity. The difference is where it sits. Ours is locked away in carbonate rock, in limestone and chalk, and the shells of things that lived and sank, buried by oceans and by the slow recycling of the crust. Venus's is in the air. The two planets were handed similar inventories and disposed of them differently, and the entire difference between a temperate world and a furnace comes down to that question of storage. The uniformity is what makes it feel so implacable. There is no cool place on Venus. Day side and night side are the same. Equator and pole are the same. The highlands are marginally cooler only because they stand higher in the atmosphere, the way a mountaintop is cooler here. Everywhere else, it is the same temperature, everywhere, always, and has been for a very long time. At that temperature, lead is liquid. So are tin and zinc. Ordinary electronics fail within minutes because the semiconductor materials we build them from stop behaving like semiconductors when they get that hot. Conventional lubricants break down. Seals soften. Adhesives release. Plastics are simply gone. Almost everything in a normal machine is disqualified before it arrives. Then there is the weight of the air. 92 times Earth's sea level pressure is equivalent to about 900 meters of water depth. That is deeper than the crush depth of any military submarine ever built, by a comfortable margin. It is a pressure that has to be designed for as the primary structural requirement, with everything else arranged around it. Several early probes did not survive the descent. They were built to fall through the atmosphere and were destroyed on the way down, imploding in the air before they ever reached the ground. The ones that succeeded were built as pressure vessels first and spacecraft second, thick spheres of titanium, insulated, pre-chilled before entry so that they had a margin of cold to spend on the way down. What those machines found is one of the more remarkable descriptions of any place anywhere. Down there, the atmosphere is dense enough that it stops behaving like a gas in the way we understand gases. Near the surface, it is closer to a fluid, thick enough that objects experience real buoyancy in it, thick enough that sound carries strangely, thick enough that the slow surface winds, only a few kilometers per hour, push with the force of a current in water rather than a breeze in air. And the light bends. The air is so dense that its refractive index becomes significant, curving the path of light noticeably over distance. The horizon does not fall away as it does here. It appears to curve upward, so that standing on Venus would feel like standing at the bottom of a shallow bowl, with the ground rising gently in every direction and the sky a dim orange lid above it. The descent itself is a journey through several distinct worlds stacked on top of each other, and it is worth following down. At the top, 100 kilometers up, the air is thin and extremely cold, colder than anywhere on Earth. Below that comes the upper haze, then the main cloud deck, spanning roughly 45 to 70 kilometers, where the pressure and temperature pass through the narrow band we will spend the next part of this video on. Beneath the clouds, the air clears, and from about 45 kilometers down to the ground, the atmosphere is comparatively transparent, growing hotter and heavier with every kilometer. The last 30 kilometers are the furnace proper. A probe falling through all of that is not descending through one environment. It is passing through a temperate zone on its way to a foundry, and it only gets a few minutes in the good part. The light down there is worth quantifying too, because it is not darkness. Enough sunlight makes it through the clouds and the dense air below to illuminate the ground at roughly the level of a heavily overcast afternoon here. It is dim, and it is deeply orange, because the long path through so much atmosphere scatters away the shorter wavelengths and leaves the reds and ambers behind. There are no shadows because the light has been scattered so thoroughly that it arrives from every direction at once. It is a flat, shadowless, amber illumination, the same everywhere, that has been falling on those rocks continuously for longer than there have been oceans on Earth. The chemistry completes the picture. Sulfuric acid in the clouds far above, sulfur dioxide throughout, traces of hydrogen fluoride and hydrogen chloride, and near the ground, a supercritical fluid state of carbon dioxide that is neither properly gas nor properly liquid. Anything sent down there has to be thermally survivable, mechanically survivable, and chemically survivable, all at once, all in the same object. The longest any lander has endured on the Venusian surface is on the order of 2 hours. Most managed considerably less. The handful of photographs they returned before falling silent are the only images ever taken from that surface, and they show flat, broken, slab-like rock under a dim orange sky, stretching away to a close horizon that curves the wrong way. That is the case for calling Venus hell, and it is a strong case. A human being on the Venusian surface would not be crushed the way a submarine hull is crushed, because a body is mostly water, and water is nearly incompressible. The heat would simply end everything, immediately and completely. The idea of a flag being planted there is faintly absurd. A flagpole would soften and slump before anyone could let go of it, and the fabric would char within seconds. But note what has and has not been established. The surface is uninhabitable. Nothing said here has any bearing on the atmosphere 50 kilometers above it, and the two are as different as the bottom of the ocean is from a mountainside. It is also worth saying that the surface may not be permanently unreachable by machines, even if it will always be unreachable by us. Silicon-based electronics fail in that heat, but silicon carbide does not. Circuits built from it can operate at Venusian surface temperatures for extended periods, and test articles have been run in simulated Venusian conditions for weeks rather than minutes. That single materials change moves long-lived surface stations from impossible to merely difficult. Mechanical computing has been seriously revisited for the same reason. Gears, cams, and levers do not care about heat in the way transistors do, and a machine that senses and records and transmits using largely mechanical means could in principle sit on that surface for a very long time. So the eventual picture may be a settled world with an uninhabited ground, where people live permanently in the air, and the surface below is worked entirely by machines that were designed for it. Material lifted from a mine 50 kilometers down to a floating city is a genuinely difficult proposition, and nobody should pretend otherwise. But it is a proposition rather than an impossibility. And the ground itself is worth knowing, because it is a real and strange place. Radar mapping from orbit, which is the only way to see through the permanent cloud, has revealed two continent-sized highland regions, one of which contains mountains taller than anything on Earth. There are over 1,000 identified volcanic structures, including broad, flat pancake domes formed by thick lava spreading slowly under enormous pressure, and lava channels running for hundreds of kilometers, longer than any river valley here. The crater record suggests the whole surface is young by planetary standards, a few 100 million years old, which implies that something resurfaced the entire planet in a relatively short episode. Whether that was a single global volcanic event or a slower process is not settled. And levels of sulfur dioxide high in the atmosphere have been observed to rise and fall over time, which some read as evidence that volcanoes are still erupting down there now, resupplying the clouds from below. There are also regions called tesserae, ancient tracts of intensely deformed and crisscrossed terrain that appear to be older than the volcanic plains around them. They may be the last surviving fragments of an earlier Venus, the crust that existed before whatever event resurfaced the rest. If any record remains of what that planet was like when it may still have had water, it is most likely written into those highlands. And Venus does all of this without plate tectonics. Earth's crust is broken into plates that slide, collide, and dive beneath one another, continuously recycling surface material back into the interior and carrying carbon down with it. Venus has no such system. Its crust appears to be a single unbroken shell. The current thinking is that heat therefore builds up underneath until it has to escape all at once, in enormous episodic resurfacing events separated by long, quiet intervals. A planet that cannot let its heat out steadily lets it out catastrophically instead, and then goes quiet again for a few 100 million years. None of that is habitable. All of it is the reason to keep looking. Part 8. The layer that changes everything. Now we go back up. Rise from that furnace, slowly, and watch what happens to the numbers as the altitude increases. At the ground, 460 degrees and 92 atmospheres. Climb 10 kilometers and both have fallen, though not by enough to matter. Climb 20 and the pressure is down to something like 20 atmospheres, the temperature to around 300. Climb 30 and it is falling faster. Climb 40 and you are approaching the base of the clouds, with the pressure down around a couple of atmospheres and the temperature under 150 degrees. And then, somewhere between roughly 50 and 55 kilometers above the Venusian surface, the numbers arrive at a set of values that ought to stop anyone reading them for the first time. At an altitude of about 52 kilometers, the atmospheric pressure on Venus is essentially identical to sea level pressure on Earth. Not similar. Not within an order of magnitude. The same. At about 55 kilometers, the temperature sits in a range running from around 0 to around 75 degrees Celsius, depending on exactly where in that band you are. Warm, certainly. Hot in places. But entirely within the range that ordinary industrial cooling handles without difficulty, and in the cooler part of the band, simply a hot day. The gravity there is 9/10 of Earth's, unchanged, because 50 kilometers is nothing set against the radius of a planet. The radiation is at roughly Earth surface levels, as we have already covered, because there are still several hundred grams per square centimeter of atmosphere overhead. And the sunlight is abundant, arriving from above and reflecting back up from the cloud deck below. Put those together, and you have this. The most Earth-like set of physical conditions found anywhere off Earth. Not the most Earth-like surface, because it is not a surface. The most Earth-like conditions, in total, of any location that has ever been measured beyond our own atmosphere. There is one consequence of this that deserves to be said slowly, because it changes the entire character of what living there would mean. A person in that layer does not need a pressure suit. The pressure outside is already correct. There is no vacuum to seal against, no differential trying to force the body outward, none of the rigid, exhausting, fatiguing engineering that a spacesuit requires. What a person there would need is a supply of breathable air, because the atmosphere is carbon dioxide. They would need protection from the sulfuric acid, because there is acid in the cloud droplets. And they would need cooling, because it is warm. Those are 3 requirements, and every one of them is met by equipment that already exists in industrial form on Earth. A supplied air respirator, a chemically resistant coverall, a cooling garment. Together, those are closer to what a firefighter or a chemical plant worker wears than to anything a spacecraft crew has ever put on. Think about what that difference means in practice, over years. On Mars, going outside is an operation. It requires a suit that is effectively a small spacecraft, a pre-breathe protocol to avoid decompression sickness, an airlock cycle, a buddy, a time limit, a dose budget, and a decontamination procedure on the way back in to keep the perchlorate dust out. Every excursion is a scheduled event with paperwork attached. On Venus at the right altitude, going outside is closer to putting on a coat, a mask, gloves, a coverall, and a door. That is not a small quality of life difference. It is the difference between an expedition and a life. It is also worth appreciating how forgiving that band is, because it is not a knife edge. The pressure and temperature change gradually with altitude, so the habitable range is several kilometers deep rather than a precise line. A habitat can sit anywhere within it and trade one property against another. A little lower gives higher pressure and more lift for the same volume, at the cost of more heat. A little higher gives cooler air and thinner cloud, at the cost of lift. Anywhere in that band, a person could survive outside with a mask. Compare that to every other candidate destination we have. The lunar surface is vacuum, 2 weeks of scorching day followed by 2 weeks of deep cold, with dust that cuts. The Martian surface is near vacuum, permanently freezing, dusty, and irradiated. The surfaces of the icy moons are vacuum, colder still, and in some cases bathed in radiation lethal within a day. The atmospheres of the giant planets have no flaw and no sunlight worth the name. Set every one of them side by side, and the Venusian cloud layer is not merely the best of them. It is in a different category entirely, because it is the only one where the 2 hardest environmental variables, pressure and gravity, are already correct without anyone doing anything. There is one more property of that layer worth naming, which is that it is stable. It is not a temporary condition or a seasonal window. The pressure and temperature at 50 kilometers above Venus are set by the mass of the atmosphere and the energy passing through it, and both of those have been essentially unchanged for an extremely long time. Whatever is built there would not be racing a closing window. It would be sitting in a condition the planet has held steady for hundreds of millions of years and will hold for hundreds of millions more. It is worth being precise about what is actually in that air, because the acid is the part people fixate on, and it deserves an accurate description. The atmosphere at that altitude is about 96% carbon dioxide and about 3.5% nitrogen, with traces of sulfur dioxide, water vapor, argon, carbon monoxide, and a handful of others. The clouds themselves consist of droplets of sulfuric acid at concentrations somewhere between roughly 75 and 98%, suspended in that gas across a deck running from about 45 to about 70 kilometers in altitude. The important word there is droplets. This is not a lake of acid, and it is not a rain in any terrestrial sense. It is a persistent fine mist, and the total quantity of liquid suspended in a given volume of air is small. The cloud is closer to an acid fog than to anything you could pour. There is something quietly strange about that rain as well. The droplets do form and fall, as rain does here. But they fall into the increasing heat below the cloud base, and they evaporate before they get anywhere near the ground, and the vapor rises again to condense once more higher up. Venus has rain that has never landed. It has been falling and unfalling in the same closed loop for an extremely long time, and not one drop has ever reached the surface. Above the main deck sits a thinner upper haze, extending well up toward the edge of space. Below the deck, a lighter haze, and then the clear, hot air of the lower atmosphere. Ultraviolet images of the cloud tops show dark streaks and swirling patterns caused by something in the atmosphere absorbing that part of the spectrum strongly. What that absorber is has never been definitively identified. It is one of the ordinary, unglamorous mysteries of the inner solar system, sitting in plain sight on the most photographed face of our nearest neighbor. There is one further thing about that layer that should be mentioned gently, without overstating it. The temperate cloud band is the only region of Venus where liquid phase chemistry at survivable temperatures exists. For that reason, the possibility that something microbial might live there has been discussed, quietly and seriously, for decades. Certain unexpected chemical signatures have been reported in those clouds from time to time, and each report has been followed by careful argument in both directions. Nothing has been established. The acid alone is a formidable obstacle for anything resembling terrestrial biology. It remains an open question rather than an answer, and it is worth holding it that way. There is a band of air around a planet next door where the pressure is right and the temperature is survivable, and we do not entirely know what is in it. What we do know is that the conditions there have been measured many times and measured well. Descent probes have fallen through that layer repeatedly over decades, transmitting pressure and temperature and composition on the way down, which is why the profile is known with real precision rather than estimated. This is not a speculative environment. It is one of the better characterized places in the solar system. It is worth pausing on what the view would be. Inside the deck, a window would show golden fog, shifting slowly, with visibility measured in tens or hundreds of meters. Rise a little, toward the cloud tops, and the fog thins into a haze and then into open sky. From above the deck, the sun is unfiltered and bright, and the cloud below becomes a luminous plane, reaching to a curved horizon, glowing where the light falls on it. Sunrise there would take hours rather than minutes, because the habitat is drifting into it at the pace of the super-rotating wind rather than being carried by a spinning planet. The whole environment would be lit from both directions at once, above and below, in a light that is gold rather than white because of what the acid clouds do to the spectrum. And something has already floated in it. 2 small instrumented balloons were deployed into the Venusian cloud layer decades ago. They inflated, they found their altitude, and they drifted with the super-rotating winds for roughly 2 Earth days each before their batteries gave out. In that time, they traveled something like 1/3 of the way around the planet, transmitting temperature, pressure, and wind data back across interplanetary space. They were small, simple, and short-lived. But they established the central point beyond argument. The idea of floating in the atmosphere of Venus is not a thought experiment. It has been done. The only questions remaining are of scale, of duration, and of what you put in the gondola. Part 9. Why a city would float. There is one fact about Venus that more than any other turns this from an interesting curiosity into an actual proposal. It is a simple piece of physics, and it is worth stating carefully because everything else depends on it. Ordinary breathable air is a lifting gas in the atmosphere of Venus. Here is why. Buoyancy is a comparison of densities. A thing floats in a fluid if it is less dense than the fluid it displaces. On Earth, we fill balloons with helium or hydrogen because those gases are far lighter than the nitrogen and oxygen that surrounds them. The Venusian atmosphere is carbon dioxide, and a carbon dioxide molecule is substantially heavier than the nitrogen and oxygen molecules that make up the air we breathe. At the same pressure and temperature, Venusian atmosphere is around 50% denser than terrestrial air, which means that a sealed envelope filled with ordinary breathable air floating in the Venusian cloud layer has exactly the buoyancy relationship that a helium balloon has here. Not as strong, but real and substantial. The lift works out to something on the order of 0.5 kilogram for every cubic meter of enclosed volume. That sounds modest until you scale it up, and volume scales very quickly indeed. A spherical envelope 1 kilometer across encloses enough air to support something on the order of 700,000 tons. That is a city by any reasonable definition of the word. But the number is not the remarkable part. The remarkable part is what is doing the lifting. On Earth, an airship has a strict separation between the gas that holds it up and the space where people are. The helium cells are sealed and unbreathable. The crew rides in a gondola underneath. The lifting gas is a resource that has to be carried, bought, and replaced, and it can never be lived in. On Venus, the lifting gas and the habitable atmosphere are the same substance. The breathable air inside the envelope is what holds the structure up, and it is also what the people inside are breathing. There is no separation. The interior volume is simultaneously the lift and the living space, which means that every cubic meter of habitat you build is a cubic meter of buoyancy you gain. Making the city bigger makes it float better. There is no other place in this solar system where that is true. And there is a second consequence that overturns the usual intuition about how fragile such a thing would be. Think about what a hole means in a spacecraft, or in a habitat on the Martian surface. Inside there is one atmosphere of pressure. Outside there is essentially none. That difference is enormous, and it wants very badly to equalize. A breach is measured in seconds, and the response is immediate and urgent. Now think about a hole in an envelope floating at 50 kilometers above Venus. Inside, one atmosphere of breathable air. Outside, one atmosphere of Venusian air. The pressures are nearly identical. There is no force driving a violent exchange. What happens instead is slow diffusion, with gases gradually mixing across the opening, and a gradual loss of lift as the interior fills with heavier gas. The habitat would begin, slowly, to sink, and the air inside would begin, slowly, to become unbreathable. Both processes measured in hours, not seconds. There would be time to notice, time to isolate the affected section, and time to go out and patch it. The picture of the repair is worth holding on to. A crew going out to fix a tier does not need a pressure suit, because the pressure is already right. They do not need a tether against explosive decompression, because there is no explosive decompression to guard against. They do not need to hurry the way anyone on Mars would. They need a mask, a cooled coverall, acid-resistant gloves, and a patch. It is closer to maintenance work than to an emergency. So what would such a structure look like? The most fully developed version of this idea was worked out in real engineering detail by a National Space Agency's Systems Analysis Group as a staged program rather than a single mission. A robotic aerostat first, to prove the deployment and the endurance. Then a short crewed visit, weeks in the cloud layer. Then a longer one. Then permanent presence. The arrival sequence is the part that sounds least plausible and is actually the most conventional. The vehicle travels folded inside an aeroshell, the same basic hardware used for entering any atmosphere. It enters, decelerates against the thickening air, sheds the shell, and inflates while still descending. The whole deployment happens in under 10 minutes, and by the end of it, the vehicle has stopped going down and started drifting. The reference design is an elongated envelope over 100 meters long, with a crude gondola suspended beneath it and solar arrays running along the upper surface. And because the habitat floats at close to 1 atmosphere with the same pressure inside and out, the gondola does not have to be a pressure vessel in the spacecraft sense. It does not need to resist a pressure differential, because there barely is one. That single fact removes an enormous amount of structural mass from the design, and mass is the currency everything else is bought with. Growth would proceed by joining modules together. Additional envelopes docked to the first, platforms built between and beneath them, rigid decks spanning the gaps, until the structure stops reading as a balloon and starts reading as a floating district. The largest speculative versions imagine envelopes kilometers across, supporting thousands of people, with open interior volume, agriculture, and genuine internal architecture. Cities in the literal sense, held up by nothing except the air they contain. The hardest unsolved piece of the architecture is getting back off. A rocket has to be launched from something, and a floating platform is not a launch pad. It moves, it flexes, and it loses lift the instant a large mass leaves it. The proposals that take this seriously keep the return vehicle waiting in orbit around Venus and send up only a small ascent stage from the cloud layer. Launching from 50 kilometers up is actually helpful in one respect, since a great deal of the atmosphere is already below you, and the rocket does not have to fight through the thickest part of it. But the platform has to absorb the departure without destabilizing, and nobody has built anything like it. This is a real engineering problem with no demonstrated answer, and it belongs on the list honestly. It is also worth remembering the sheer logistics of establishing anything at all off Earth. There is nowhere to buy a replacement part. Everything a settlement needs in its early years has to be carried there, at enormous cost per kilogram, across an interplanetary distance, in a window that opens on the solar system's schedule rather than anyone else's. This is why the mass savings matter so much, and why removing the requirement for a pressure hull, for burial equipment, for radiation shielding, and for a nuclear power supply is not a technicality. Each of those is tons that do not have to be lifted out of Earth's gravity well and flown across the inner solar system. A design that needs less is a design that arrives sooner. Several details make this more robust than it might sound. Because the lift comes from a density difference rather than a pressure difference, the envelope material does not have to be structural in the way a hull is. Its job is to contain and to resist chemistry, not to hold back force. It can be a thin, flexible membrane, which is a far easier thing to make, to fold, to transport, and to repair. Altitude control uses techniques that balloon engineering has understood for a very long time. Heat the internal gas to rise. Vent to descend. Adjust ballast. Change the envelope volume. None of it requires anything new. The arrangement is passively stable. With a heavy gondola hanging beneath a light envelope, the center of mass sits well below the center of buoyancy, which means the whole structure rights itself if it tilts. It does not need active stabilization to stay the correct way up. It simply hangs, the way a plumb line hangs. And multiple joined envelopes give a kind of redundancy that a single hull can never offer. Losing pressure in one cell of a many-celled structure reduces lift somewhat. It does not end anything. The settlement descends a little, and the crew repairs the cell. Compartmentalization on Earth's ships and airships was learned the hard way over a very long time, and all of that knowledge transfers directly. Even a serious loss of lift has a strange property working in its favor, at least at first. A habitat that sinks moves into denser air, and denser air provides more lift per unit of volume. The descent tends to slow itself for a while before it becomes unrecoverable. That is not a rescue, but it is time, and time is what emergencies are usually short of. Growing food in such a place has one obvious advantage and one obvious difficulty. The advantage is light. Plants in a Venusian habitat could be grown under natural sunlight at nearly twice terrestrial intensity, arriving continuously except for the two-day night, which is a shorter interruption than many crops experience through a terrestrial winter. Carbon dioxide, which greenhouse operators here pay to add to the air, is available outside in unlimited quantity. The difficulty is water, and we will come to that shortly, because it is the one place where this whole proposition genuinely struggles. A century of terrestrial airship engineering sits behind all of this. Envelope materials, seam construction, gas management, mooring, handling and weather. Much of that hard-won knowledge was set aside when airships stopped being useful here. It turns out to have been waiting for a different planet. Part 10. Acid, water, and what breaks. The most common objection to everything described so far is the acid, so it is worth taking it seriously and then setting it in proportion. The sulfuric acid in the Venusian cloud deck is real, it is concentrated, and anything left exposed in it without protection would be degraded. That is a genuine engineering constraint, and it would shape every external surface of a habitat. But it is also, on inspection, the most tractable of the problems in this comparison, for a straightforward reason. We handle concentrated sulfuric acid in enormous quantities on Earth, every single day, in tanks and pipes and reactors, and we have known how to do it for a very long time. The materials that resist it are well established. Certain fluorinated polymers are effectively immune, which is why they line acid tanks here. Glass and many ceramics resist it indefinitely. Gold does. Several specialized alloys do. None of these are exotic laboratory curiosities. They are industrial materials with supply chains and standards behind them. An envelope design therefore assumes a laminate rather than a single material. An acid-resistant outer skin, a structural layer beneath it that never sees the outside, and a gas barrier within that. Metals that corrode readily simply stay inside or are coated. Exposed hardware is polymer, ceramic, or deliberately sacrificial and designed to be replaced on a schedule. And the habitat can choose where to sit. The clouds thin out below about 45 kilometers and again above about 70. Altitude is a chemistry decision as well as a pressure decision, and there is a range to work within. It is worth comparing this to the Martian equivalent, because both worlds have a chemistry problem, and they behave very differently. The Martian soil contains perchlorate salts at levels toxic to humans, and the dust is fine, abrasive, and electrically charged. It clings. It comes in through the airlock on every suit, in every seam and fold, and it has to be managed with elaborate cleaning protocols that never end. Venus's chemistry stays outside. Mars's chemistry comes indoors on your boots, every single time. Now the part where Venus genuinely and seriously loses. Venus is extraordinarily dry. Its atmosphere holds only traces of water vapor. Its surface has none. There is no ice, no permafrost, no buried glacier, no hydrated mineral deposit waiting to be quarried. Water, which is the single most important substance for keeping human beings alive, is close to absent. There is a route to it, and it is a clever one. The clouds themselves are sulfuric acid, and sulfuric acid is made of hydrogen, sulfur, and oxygen. The hydrogen can be liberated chemically. The carbon dioxide of the atmosphere is an unlimited source of oxygen. Combine the two and you have water, manufactured out of the sky. That process works, and it has useful byproducts. It yields sulfur, which is industrially valuable, and oxygen in excess. But it is energy intensive, and the water comes slowly, gathered droplet by droplet, out of an atmosphere that holds very little. Mars, by contrast, has water in quantities that make the problem almost boring. Ice at both poles in enormous sheets. Buried glaciers at mid-latitudes, some hundreds of meters thick, under a protective layer of dust. Hydrated minerals distributed across wide regions. On Mars, water is a mining problem, and mining is a solved category of problem. You dig, you heat, you collect. The reverse is true for nitrogen, and this is less often noticed. A breathable atmosphere is not pure oxygen. It needs a buffer gas, and nitrogen is the one we evolved with. Venus has more nitrogen in its atmosphere than Earth does in total, freely available. Mars's thin air holds very little, and every gram of it would have to be extracted from an atmosphere that barely exists or shipped from Earth. Oxygen itself is straightforward on both worlds, since both atmospheres are overwhelmingly carbon dioxide, and splitting carbon dioxide into oxygen and carbon monoxide has already been demonstrated on the Martian surface by a small experimental device that ran successfully many times. So the resource picture splits cleanly, and it splits in a way that mirrors everything else in this comparison. Venus has energy, nitrogen, carbon, and sulfur without limit, and almost no water and no accessible metal. Mars has water, iron, aluminum, silicon, magnesium, titanium, and every mineral a surface can offer, and comparatively little energy and almost no nitrogen. Hydrogen is the crux. It is the scarcest common element on Venus, and it is the element that everything biological and much that is industrial depends on. An early Venusian settlement would likely have to import it from Earth or eventually from icy bodies elsewhere in the solar system until the acid processing chain could carry the load. That is a real dependency and a real vulnerability. Carbon, meanwhile, is unlimited there, which means carbon-based materials, polymers and carbon fiber among them, could in principle be manufactured locally in quantity. A settlement that can make its own structural composites out of the air around it is in a considerably better position than one that cannot. In fairness to Mars, its perchlorates are not purely a hazard. They are chlorine and oxygen bound together, and some processing schemes treat them as a feedstock rather than a contaminant, extracting useful oxygen and useful chlorine from soil that would otherwise have to be avoided. And the deeper advantage remains untouched. Everything on the Martian surface can be reached with a shovel and a rover. Iron, aluminum, silicon, magnesium, titanium, all of it lying in the open, at ambient temperature, waiting. A floating city cannot reach any of that without lowering something 50 kilometers into a furnace and hauling it back up. Robotic surface mining on Venus is not impossible, particularly with the high-temperature electronics now becoming available, but it is an enormously harder proposition than driving a machine across a plain. Now, what actually goes wrong in each place? On Venus, the failure modes are mostly slow. A gradual loss of lift from a leak, which lowers the habitat into hotter and denser air, buying a little time from the increased buoyancy before the heat becomes the problem. Structural failure at a joint between modules, which stresses the remaining envelopes and is mitigated by keeping them separate. Acid degradation of exposed surfaces, which is relentless but predictable and answered by inspection and replacement. Loss of power, which matters because the cooling stops. Drifting into a polar vortex or an unfavorable altitude band, which is a navigation problem with a navigation answer. And one failure mode with no answer at all. There is nowhere to set down. A habitat in serious trouble cannot land, cannot be evacuated to the ground, cannot wait somewhere safe while it is repaired. There are exactly two options: fix it or move everyone to another floating structure. That is the hard limit of the entire concept, and it should not be minimized. On Mars, the failure modes are mostly fast. Pressure loss in a habitat is measured in seconds because the outside is effectively vacuum. A dust storm can cut power for weeks with no warning of how long it will last. A solar particle event requires everyone to reach shelter within a narrow window. Dust and perchlorate contamination is chronic and cumulative. And underneath all of it, the slow decline in bone and muscle and cardiovascular capacity that never stops and has no acute moment to respond to. But Mars has the one thing Venus cannot offer. It has ground. A crew whose habitat fails can put on suits and walk to another one. They can shelter in a cave, bury themselves, wait. The surface is a fallback, and a fallback is worth a great deal when everything else has gone wrong. That difference produces two very different kinds of life. The Martian settler lives in a buried structure under several meters of soil, at a third of their proper weight, with dust in every seal, going outside in a suit against a dose budget, under a pale butterscotch sky over a close and rock-strewn horizon. The Venusian settler lives in a bright, warm, nearly Earth-weight interior, in continuous sunlight, stepping outside onto a deck in a mask and a cooled coverall, under a golden overcast, above an ocean of cloud, with nothing solid beneath the floor. Ever. Which of those a person could bear for decades is not an engineering question. It is a human one, and different people would answer it differently. There is no precedent for the second kind of life, though there are partial ones. Sailors, submariners, and long-duration crews all live inside environments that would kill them a meter away, and they manage. Confinement studies consistently find that the dominant psychological stressors are not danger, but monotony, lack of privacy, and friction between people. But nobody has ever spent a lifetime with no shore anywhere, on any horizon, at any depth. That is genuinely new. Two smaller differences would shape daily life in ways that are easy to overlook. The first is the delay in talking to Earth. On Mars, conversation is impossible as a matter of physics. Every exchange is a message with a weight attached, and a settlement there would be psychologically alone in a way no human community has ever been. At Venus, at closest approach, a 5-minute round trip permits something clumsy but recognizable as a conversation. That is not nothing when a person is homesick. The second is the rhythm of the day. Mars gives an almost perfect 24-hour cycle, which is a real and underrated gift to a human body. Venus gives a 4-day one, 2 days of light and 2 of dark, drifting with the wind. People in isolation experiments have adapted to non-standard cycles with mixed success, and a habitat would probably run internal lighting on a 24-hour schedule regardless of what the sky was doing. But the sky would be doing something else, and living under it would take adjustment. What is known is that views matter more than mission planners expect. Crew members consistently rate windows and the sight of home among the most valuable things available to them. And a habitat drifting through a golden cloud layer, lit from above and below, with sunrises that last for hours, is not a small thing to be able to look at. Part 11. The Long Horizon, and Which One? Both of these worlds attract schemes for transforming them completely, and both sets of schemes are far beyond anything we can currently do. They are worth walking through anyway, gently, as a way of seeing what each planet's deepest problem really is. Not as prediction, as a long thought held loosely. Mars is too small, too cold, too thin, and too exposed. The obvious first step in warming it would be to release the carbon dioxide currently locked away, frozen into the polar caps, and absorbed into the soil across the whole planet. Warming Mars would release some of it, which would warm it further, which would release more, and in principle, that feedback could run in the direction we wanted for once. The difficulty is inventory. Careful accounting of how much carbon dioxide is actually accessible on Mars suggests the total falls far short of what would be needed to produce a meaningful atmosphere. Not slightly short. Short by a large factor. There is simply not enough of it left on the planet, because most of what Mars once had was stripped away long ago and is now scattered through interplanetary space. Anything added would eventually be stripped again, since Mars has no magnetic field to protect it. Though that particular objection is weaker than it sounds, because the stripping operates over tens of millions of years. On the timescale of a civilization, it is a maintenance issue rather than a fatal one. There have been serious studies of placing an artificial magnetic shield at a stable point between Mars and the Sun, generating a field that would drape around the planet and deflect the solar wind. It is an enormous idea, and it is not an absurd one. But the gravity would remain. Whatever else were done, however thick the air became, however warm the ground, a terraformed Mars would still be a world where a human body carries a third of its proper weight, with every question from earlier in this video still unanswered. Venus has the opposite problem, and it is opposite in every respect. Not too little atmosphere, but far too much. Not too cold, but far too hot. The task is not to add, but to remove, and the quantity involved is difficult to hold in the mind. An atmosphere 92 times as massive as the entire air of Earth, almost all of it a greenhouse gas. 3 broad approaches get discussed. The first is chemical, fixing the carbon dioxide into carbonate rock, the way Earth's oceans and crust did with ours. This works in principle and requires calcium and magnesium in quantities comparable to a substantial fraction of the planet's crust. The second is thermal, placing an enormous shade at the gravitationally balanced point between Venus and the Sun, cutting the sunlight and letting the planet cool over centuries until the carbon dioxide begins to condense out of the sky and fall as snow. The third is chemical in a different way, delivering enormous quantities of hydrogen to react with the carbon dioxide, producing graphite and water, which would leave the planet with both a thinner atmosphere and the oceans it lost. All of these are centuries away at the very least, and probably much further. But there is a detail worth noticing about the Venusian version. A sunshade also solves the rotation problem. Venus's slow backward spin is usually listed as an obstacle to habitability, but if the light reaching the planet were being regulated artificially anyway, the length of the day would matter far less. And at the end of it all, a transformed Venus would have Earth's gravity. Not approximately. Essentially, exactly. That is the one thing no amount of work will ever give Mars. There is a more modest version of the Venus idea that may be the most realistic of all of them, and it does not involve transforming anything. It is simply this: live in the clouds permanently and never touch the ground. A settled world with an uninhabited surface. The floating cities go on drifting, generation after generation, and the furnace below is studied by machines and otherwise left alone. That is not terraforming. It is something more like accepting a planet on its own terms and finding the one part of it that already suits us. It is worth saying that the near-term version of this is not expensive by the standards of anything else discussed here. A balloon carrying instruments into the Venusian cloud layer is a modest mission by modern spacecraft budgets, far cheaper than putting a rover on Mars, and far cheaper still than the machinery of a crewed landing. The precursors are affordable. That has been true for a long time. And interest has genuinely returned. After decades in which Venus received almost no attention, a new set of orbiters and atmospheric probes is being prepared by several space agencies, aimed at mapping the surface properly, sampling the cloud chemistry directly, and settling several of the open questions that have sat unanswered since the early era. Whatever anyone eventually decides to build there, the atmospheric data those missions return would be the foundation it rests on. There is also the argument that goes the other way, which is that Venus is good practice. Much of what a floating habitat would teach us about closed life support, about long-duration cruise far from home, about materials in a hostile chemistry, transfers directly to any settlement anywhere. Most of the current conversation, when Venus comes up at all, treats it in exactly this way, as a rehearsal for somewhere else. The instinct to plant a flag has not been overcome. It has just been postponed. What is encouraging, in a quiet way, is that the unsolved problems of the floating city concept are now specific rather than vague. Where does the hydrogen come from? How long does an envelope last in the acid before it needs replacing? How do you launch a return vehicle from something that floats? Those are three named engineering questions with people working on them. A proposal whose remaining objections have names is in far better shape than one whose objections are simply a feeling that it sounds strange. So, which one? The honest answer is that the comparison does not produce a winner, and pretending otherwise would be a disservice to both worlds. What it produces is a clarification, and the clarification is worth more than a verdict. If the question is where a human body can live well for a lifetime, the answer is Venus, and it is not close. Correct gravity, correct pressure, radiation at roughly the level of a mountain town, sunlight in abundance with no dust and no seasons, a shorter journey each way, and no need to put on a spacecraft in order to step outside. Every variable that determines whether a person remains healthy over decades comes out in Venus's favor, and the single most important of them, weight, comes out overwhelmingly so. If the question is where a civilization can become genuinely independent of Earth, the answer is Mars, and that is not close either. Water in enormous quantities. Metal, silicon, and every mineral a crust can supply. Room to spread horizontally without building anything. Ground to stand on when things fail. A day the length of ours. Everything a society needs in order to stop needing anything from home. Perhaps the most defensible position is that Venus is the better destination and Mars is the better colony. That the two worlds answer different questions, and a species serious about leaving this planet would eventually want both, and would probably want the easier one first, because that is how anyone sensible learns anything. What is much harder to defend is the situation we actually have, in which one of them receives all of the planning, all of the funding, and all of the imagination, and the other receives almost none. That imbalance was not produced by a careful comparison. It was produced by a story that got told first, by a disappointment that landed hard, and by a very old instinct that says a place does not count until you have stood on it. There is a version of this that is almost funny, if you hold it at the right angle. We named one of these planets after the goddess of love, looked at it once, and decided it was hell. We named the other after the god of war, and decided it was home. Neither name had anything to do with what we found. But the names have outlasted the findings, and they are still quietly doing work in every conversation about where we go next. Somewhere 50 kilometers above a furnace hot enough to melt lead, there is a band of air where the pressure is exactly what a human body expects, where the weight underfoot is 9/10 of what you feel right now, where the light comes from above and below at once, and everything is gold. It has been there for hundreds of millions of years. It will be there for hundreds of millions more. It has never once appeared in a national space policy. We may go there eventually. We may not. The physics does not care either way, and neither does Venus. And so we leave it where we found it, turning slowly backwards beneath its unbroken cloud, holding one narrow ribbon of air that would suit us better than anywhere else we have ever looked, waiting without urgency to be noticed. Whether anything is ever built there is a question for other nights, and it will keep. Let your breathing slow. Let the weight of the day settle out of you. Sleep well, and good night.